All right, so previously we looked at the electric fields, and electric fields is essentially just a study on how charged particles interact with each other. And we specifically focus on the parallel plate and also the four pillars. Okay, so it's important to also think about how the pillars connect to each other. So feel free to refer to the recording for that. Today we're going to continue on with capacitor, which is essentially a application of electric fields. So we're going to look at capacitance as sort of like a side quest, a side case study on how we can use a different circuit component and how it behaves in a circuit, but not too much in detail, right? Just bits and parts of it only. So, hmm, excuse me. All right. So you know how when you were in your AS, you studied the resistor, and the resistor looks like this, and we call it the resistor. Whose job in a circuit is to resist charge flow. So whenever we build a circuit, right, no matter how simple or how complicated it is, every single component has a reason to be there. There's a role. Either is to measure something, or like for the resistor, is to resist charge flow, uh, and also to convert energy. All right. But either way, because resistor is there to resist charge flow, the value of its resistance measures its ability to resist charge flow. So for example, if I have R is 10 ohm versus R is 20 ohm, I know 20 ohm is doing a better job compared to 10 ohm at resisting the current flow or the charge flow. Okay, so moving on. Today we're going to get to know a new component. It's called a capacitor, C. So in terms of its English, you will see the OR here. And the role of the capacitor is to basically store energy. Store energy, or we can call this to separate charges. Okay. Colloquially, meaning if we're just, just chatting and not caring too much about the scientific notation, I can actually say the capacitor store charge on one plate. So if you want to think about it as storing charges, it is on one of the plates. Okay, so in Cambridge, they generally don't recommend you talk about this. They want you to talk about the energy storage. Okay, so in this case, we will have capacitance. So again, look at the tons at the back. So again, the larger the value of C. So let's say I have C is 10 microfarad versus C is 20 microfarad. The larger the C, the better it is, or the easier it is to store energy. All right. So when we define capacitance, C, we define it as the ratio of charge stored in a single plate of a capacitor to the potential difference across the capacitor. So your C is the ratio of Q over P. When we store charges, right, what we're going to do is we would connect this to a power supply. And what the power supply does is it looks at the charges and go, these two plates are neutral, right? So let's take the electrons away from this plate because it's attracted to the positive terminal and deposit them on the other plate. So this plate will be more and more negative. As this other plate becomes more and more negative, the other plate is more and more positive because electrons are removed. When we start, before any of this, they are neutral, meaning they have equal number of positive and negative charges, neutral. This is how it begins. But because we connect to the battery wants to try to set up a potential difference between the plate. That's the job of the battery. Its job is to make sure everything connected across it is the EMF. So thanks to the battery, we won't get this. The negative charges will move to one side, making this side negative. And because the charges are removed from one of the plate, the other plate will be charged positive. This allows us to set up a potential difference across the plate. And this will continue until V is equal to EMF E. So let's say I install a voltmeter here. I can measure V, the potential difference across the plate. And the reading for my V against time will look something like this. Eventually, it will plateau and it will reach the EMF E. Okay. And the amount of charge separated on one plate is positive Q and the other plate is negative Q. So that's the charging mechanism of a capacitor in a nutshell. We have a lot of graphs that we can draw from here. I'm just going to leave it as this graph for now. Okay. And from this equation, capacitor C is obviously a scalar quantity, is a ratio. Okay. And the unit we're going to use is farad, F. There are some factors that will affect the capacitance. For resistor, we know it's rho L over A, which kind of makes sense because the larger the area, the harder it is for current to flow. And then the longer the wire, the harder it is for current to flow. So in this case, if I want to store charges or I want to separate the charge, it's easier for me to deposit the charges here if I have a larger area. Because every electron that I add to this plate means that I need to push away all the other electrons to make space for it. So when area increase, it is easier to store charge. Capacitance increase. If you want the equation, C is inversely proportional, directly proportional to area. Okay, plate separation, here to here is your X, how far the plates are. So if the plates are closer, it is easier. It's like these negative charges will help the battery push the electron away from the positive plate. Does that make sense? Because your neighbor, your opposite plate is more and more negative. So in this case, when X increase, when they are closer, when they are further apart, capacitance decrease. So C is inversely proportional to the separation X. And of course, this one is a type of insulator in between the capacitor. Because currently, I didn't mention anything, but right between this plate is an air gap. It can be anything. I can make a ice cream sandwich from two metal plates and some silicone or some ceramic. Most of the capacitors in the practical circuits in your life uses ceramic. So in between here is an insulator, but in your syllabus, we only use air. Okay, so I'm just going to add that in. Epsilon not. So when epsilon increase, capacitance increase. So different type of material will have different capacitance. Putting all of these together, you have C is equal to epsilon naught A over X. This is not in syllabus. You need to know the factors because it came out once only in winter 2-1. So I got a bit paranoid, so I just add it there in the notes lah. Just FYI. But if they want you to apply the concept, it's not so much like they want you to use the new equation, but more so they want you to be able to tell, okay, now I bring the plates closer, what happened to the capacitance? Or I bring the plates or use a larger plate, what happens to the capacitance? Okay, uses of capacitors are as follow. The main use we're going to look at in this topic, or rather this chapter is the first one, to store electrical energy and to use it as a timing circuit, because this one we can study or we will study the discharging capacitor. It can be used to block direct current because once the potential difference across the capacitor is equal to the EMF, no current flow. Capacitor full. Not the power supply can no longer give energy for the next electron to put here. Every time I squeeze another electron in, I need energy. Sooner or later, the amount of energy needed will be the same as the energy that I have. That will be the equilibrium position. So no current flow. All right. Smoothing your rectified voltage, if you already learned alternating current topic in your college, which you should have by now. This one, we will look at it in chapter 20. 20, 19, 20, 21. Rectified AC. So this is a common combo lah. They can ask you about rectified AC, followed quickly by a capacitor question. Okay, so we learned to define the capacitor, we learned the factors that affect capacitance, we learned the uses of capacitor, right? Then we're going to look at the energy stored in the capacitor, okay? Because when your switch is closed in your circuit, so I'm going to just, instead of drawing like a one with a fully sliced parallel plate, the capacitor kind of look like this lah. See, okay?